Hi, the section 8.6, robust estimation. So parameter estimates are affected severely by outliers in general. So the situation is like this. So suppose we have the likelihood function and we optimize beta. But if xi is really extreme, then the likelihood function becomes very small. So that means that we have to determine beta so that the outlier xi that does not make the likelihood function too small. So the beta hat is adjusted too much by the outliers. So we would like to mitigate the effects. And the one way is we put the lower weights to outliers. So originally that we have the equation to solve for the parameters, that is the summation of I of the yi minus mu I over the variance of mu I, the times the d mu I d beta j for the each j. So basically this function is good because the expectation of this function is 0. So if we have a large sample size, so I is equal to 1 to n, and n is large, then basically the solution of this, the first equation, that goes to true beta. But now that we would like to put some weight parameter gamma I, so that if the yi is an outlier, that we would like to put a lower weight for this. But if we put some artificial weight here, then expectation that may not be 0. Because this is no longer maximum likelihood estimator and doesn't have the many good properties. So here, the idea is that we would like to adjust this likelihood function by putting this weight gamma I, but most of the time we would like to expect this is still the unbiased. So conditionally, the unbiased influence function method that avoids the bias when there are no outliers. So so if there are outliers, that we should put some gamma I to reduce the effects of outlier. But if no outliers, we would like to make this estimator still the unbiased. So the idea is that we just modify the likelihood function for just extreme x. So think about the same curve as the upper right figure, and we have the xi, and we have some outlier. Maybe I would say the set of xi and yi. I would say this should be the observation. So xi, yi. Maybe I should say yi or. Yeah, so but if xi or yi is extreme, then the likelihood function becomes too small. So the idea is at some point, we just reduce the effect and we use just a straight line. So if observations are within the normal range, the usual range, that we don't change the likelihood function, but we just change the likelihood function for the outside. So here and here, we change the likelihood function. So this is the so-called Hoover type error function. So we at least reduce the effect of outlier. So often this red curve is the quadratic function, but we just use the linear function outside of some range. So in this way, since the likelihood function is not affected if the observations are not outliers. So if no outliers, still we have the good properties for beta hat. So we don't discuss the detailed algorithms, but we have just one example. So remember the Galapagos Islands data. So we have the number of species in each of the islands and also some other predictors. And we fit the species, the number of species on the log of area and the log of area of adjacent island. Then we get intercept and the coefficients for log of area and log of adjacent. And okay, so estimates 3.27, 0.38, and the negative 0. Maybe 10. Standard deviations are pretty small and values are very significant. And if we wanna use the robust estimator, we have to use the different function, the glm rob function. This is in the package, the robust base function, robust base package. The textbook says the robust package, but the robust package does not include this function. Okay, then the estimates are here. And of course, we use the different error function, so different function to maximize or minimize. So the estimation results are slightly different. Still, it's similar, but the 0.37 becomes 0.42 and negative 0.10 becomes negative 0.11. And also the intercept 3.28 becomes the 2.98. So, and standard deviations, still the similar size. And the z-values are also similar, but then we have a slight difference because estimation methods are different. So now that we would like to see the benefit of robust estimator, so I just artificially made one outlier. So originally, the original data, the first line that we have, there are 58 species. Generally, the number of species is such as maybe the 5 to 100, but we just make 58 into 5800. Then what happens? Then outliers, this outlier affects the estimation results much if we use usual estimator. And actually, if we use usual, the GLM, the estimates become pretty different. So originally, the first one was the 3.28, and the second one is 0.37 or 38, and the third one is negative 0.10. And maybe third one is still similar, but the second one, the size almost becomes half. And the intercept also changes a lot. But if you use the robust estimator, the intercept 3.12, this was originally the 2.98. And the second one was originally the 0.42, and the third one negative 0.11. So it doesn't change much. Maybe 0.42 becomes 0.40, but still it's similar, even though this outlier is the very extreme, the 100 times larger. So you can see that the robust estimator gives the more stable results if there are some measurements error or even the true errors, but the outliers.